Okay, so this is what I'm going to do. I'm going to open the prompt and I'll call Jupyter Lab.
Are you sharing your screen, please?
Oh, I haven't done that yet. Oh, sorry. Let me check. Share screen. Okay. Can you see my screen? Oh,
yes.
then again. Okay, sure. So we are not in pandas, we are coming to machine learning. Okay. So what is this? Oh, sorry. This is what I was doing for the exam officer. Then I document and so that is supposed to be, which one is it? This? Yeah, I think it's this one. So yes, today we don't have a lot of slides. Let me try and get my data into the appropriate directory so we can start working with it. Let me push this guy. Okay, good. So this is the data we'll be using for today's class. Let me grab it and push it to okay. Let me drop the data here. Okay, good. So this is the data we'll be using. Okay, we have this set of data here, which is more about a company that deals in housing, more like real estate. Okay, so we have the prices of the various houses, and these are a few properties or characteristics of the various houses. So of course, we don't know the name for this house. All we know is that the house is priced about 13 million. Then this is the area the house covers, the number of bedrooms, bathrooms. There's a 3-story building and it's along the road and it doesn't have a guest room. So what this data here is that given that we have a house with this space, bedroom, bathrooms, story, if it's along the main road and then has got a guest room or not. This is how much the price is. So we have a lot of houses over here with several properties or characteristics, and then we have their prices here. Now, what we want to do is to be able to build a machine learning algorithm such that if I'm going to the market, okay, the real estate market to try and then get a house for myself. Now, assuming the house has got this area, this number of bedrooms, bathhouse, and is by the roadside, 4-story, and then it doesn't have any guest room. What is my best guess for the price? Okay, and what we're expecting the AI model to do is to predict the price of that building before we even get it. So this is what we are going to do. Building AI models doesn't apply to only houses like that. It applies to every single thing that can be converted to numerical form. So if you have images and you want to be able to predict an image or something, so long as you can convert that image to a number or numerical value, you can run a machine learning model. So any single thing you can convert to numbers, you can actually build machine learning models around them. Okay. So quickly, I think we have a short insight about the data we'll be working with for today. So let me go ahead and then open the slide so we can follow it. Okay. So as usual, I have some disclaimer here. I'll be using some images that do not belong to me. I didn't develop those images. I picked them from Google. Okay. All right. So Okay. Where is that one coming from? Okay. All right. So machine learning. Have you heard anything about machine learning, and what did you hear, or what do you know about it? Just forget about what we have here, and then um, tell me what you've heard or know about machine learning. Anybody can come in and then talk.
Hello.
Yes.
What I know about machine learning is an intelligence that helps businesses to grow through models. That's all.
Okay. Is this Christy?
Yes, please.
Oh, okay. All right. That's fine. And any other person?
Yeah, Pastor.
Yes.
So, generally, what I know about machine learning is more or less a system that can automatically grab information and improve on that information by using algorithms.
Okay. That is also interesting. I think we've had different perspectives of what machine learning is about. But I'm going to explain what machine learning is with some illustration or an example. If I have maybe, let me pull up Notepad. Okay, so we are going to continue from where we ended yesterday. And, so let's make this assumption. Okay, I have some record, say 2, then dash 2. And I write here 4. I have maybe 3, dash maybe 3. I write here 9. I have 4 dash 4. I have here 16. I have here 9 dash 9. I have here about 81, and I have 7 dash 7. I have here about 49. Now, can anybody look at this one and then tell me what's actually happening here?
You are squaring the numbers.
I'm squaring the numbers.
Yes.
Okay, so someone is saying that I pick this number here, then I square them, and that is what I get here. So it means 2 to the power 2 is 4, 3 to the power 2 is 9, 4 to the power 2 is 16. So how did you get to know that I'm squaring the numbers?
So I was saying just multiplying the numbers, the first and the second number.
Okay, I think it's basically the same thing. The square is like that same number 2 times. If it is cube, that same number 3 times. So it's no different from maybe squaring them. But I want to know how you manage to know that I was squaring this to get these values. Yes, Nancy.
Pasty, you are giving lots of let me say examples. Okay, and you can recognize the pattern from all those examples you are giving. So it's easy to tell that you are squaring it.
Okay, so in this case, can we say your brain is acting like some kind of intelligence over here? I don't know how to call it, but your brain is being intelligent at this point. Yes.
Yes,
So
very much so.
So you come to realize that nobody told your brain that this is what's happening, but it was able to recognize a particular pattern in it. And so therefore, if I'm able to put something like 1 over here, and I want to predict what the response will be, what is your brain going to tell you about this? Your brain will say, oh, the result is probably 1 because 1 to the power 2 is the same as 1, right?
Yes.
So, But you see, this one here, what we're trying to do is about human brains, using our brains to recognize some of these patterns. Now, in the case of machines are not humans. I can say they don't have brains, but of course, maybe people tend to call maybe the CPUs and the likes as their brains, or maybe the system units as the brain of the computer. That's fine. But we understand that the computer doesn't have any kind of brains like ours. It is just a machine. And now, this machine here, when we give the machine this data here, the machine will be able to look at it and say, oh, we had 2 here, and then we had 4, 3 here, it had this. Now, it comes down to some mathematical rule or statistical rule to try and then find a relationship between these values, which happens to be the independent value, and then these results, which happens to be the dependent. So the machine's best guess is going to say that, hey, we have x, and then it is x to the power 2. And so this is going to predict whatever thing we have. And so therefore, the machine is going to come out with a simple rule saying that, hey, this is actually a function of x. And that function is, if I pick whatever number you are bringing in, now square it. So the computer is going to look through this one and then come out with this pattern. You know that this is a pattern, right? I hope you know that this is a pattern. This thing here, this function here is a
Yes.
pattern.
Yes,
Yes.
Yes, sure.
yes, Pasty.
Obi maths nye adwuma nti onim say a pattern. It's fine.
Hey, Pasty.
So this is actually a pattern. It means if I throw a particular number here, x, in here, it is going to result in this. Or because we have 2 different numbers, we can say we have a function that accepts 2 numbers and it gives me a result. So what is this? This is x, and then we are going to pass that same x to it. So we pick those 2 numbers, and what we are trying to do is to multiply those 2 numbers. So the machine is going to be able to recognize some of these rules. But remember, we did not maybe say manually come out with a formula for this, but it was as a result of we observing some pattern in the independent variables and the dependent variables. And that is how come we came up with this. Now, that's the exact same thing the machine tries to mimic. Okay, the machine is just behaving like human brains. Okay, you give it some data, it tries to look through the data to come out with the pattern it's observing, and then based on that pattern, you give it a new set of records that it hasn't seen before. It is able to make a projection that, hey, with this input ABC, I think the result is going to be this, based on the patterns I've recognized in the previous data. Does that make sense?
Yes.
Okay, sure. So let's hide this guy here for now. So that is everything about
Yes,
machine learning. Okay, but just that we have different categories or types of machine learning, where we have maybe deep learning models and the likes. Okay, deep learning is actually machine learning. We just try to give it a different name. But can anybody tell me the core difference between machine learning and deep learning, assuming you've heard about deep learning? Anybody with an idea? Or you haven't heard about deep learning before? Are we there? I'm off.
You are not off.
Okay.
Pasty, can we say
Yes.
that deep learning is more or less
You're not of course you're here.
a subset of machine learning?
Okay, so someone is saying that deep learning is a subset of machine learning. But my question here is, I'm interested in the difference. Why would someone want to learn, let's say, the natural machine learning models that we know, and then at the same time learn, say, deep learning, more like using neural networks and the likes? Why would someone want to do the two? Now, the core difference here is that when we are working with pure machine learning models, okay, Nancy wants to say something.
Okay, Pasty, I was going to let you. Okay, let me just share an opinion, okay?
Okay.
you see, with machine learning, we are usually trying to, excuse me, with machine learning, you see, we are usually trying to give the system like rules, like the patterns you should follow, the algorithms. But with deep learning, the system automatically learns the rules and the patterns from the data itself.
Okay.
That's what I know.
Okay, that's fine. So the whole business of both machine learning and deep learning is that we don't specify the rules. Okay, we do not specify the rules. The computer tries to identify the pattern by itself. So both machine learning and then deep learning, we don't specify the rules. But I think I understand where you were coming from. What you wanted to say was that when we are training the model, we tend to give the model some columns to learn from it. And then out of those columns, it is able to make some projections. And then we have instances where we don't even provide specific columns it should be learning from. We just provide the entire data to it and it's able to do its own thing. But we'll come to that. It is a type of machine learning. Okay. All right. Now, the core difference between machine learning and deep learning is that deep learning models work better on non-numeric values. And then machine learning models work better on numeric values. So for example, the housing data we have over here is more numeric in nature. And so therefore, machine learning models are very good at it. Now, if you want to use a machine learning model to build a natural language processing system, you are going to struggle a bit. Of course, you can do it, but you struggle a bit. Now, deep learning models were built with that in mind. And so therefore, if you want to build a natural language processing system, you may want to reach out to deep learning models other than using the traditional machine learning models. So here's the difference. Machine learning models are good with numerical data, and the deep learning models are good with unstructured kind of data, which is not numeric in nature. Okay, I don't know if this is able to clear or come out with some clear distinction between the two.
Yes, please.
Okay, sure. All right. Now, in machine learning, we usually find ourselves doing one of three things. Sometimes people argue that it is four, but we'll see if we have four. But that will be dependent on your opinions and then specifically what you want to do. Now, we have instances where you are going to indicate which columns the machine or the model should learn from, and then which values is supposed to be predicting. So you're going to give it examples of the columns of interest, okay, and examples of what it should be predicting, okay. And with that one, we call it supervised learning. So the model actually learns from labeled data. So we have column A, column B, and then we are saying that, hey, column A is my independent variable, which is X, and the column Y is the dependent variable, which is the Y values, okay? And so therefore, look at the X values and then tell me what is going to happen in the Y values. And that actually happens, and we call that supervised learning. Now, the unsupervised learning, we don't actually provide specific labels to it, okay? So if you are trying to build a model where you will not be providing specific labels to tell the machine that learn from column A, column B, and column C to predict D, they will call that unsupervised learning. Now, we also have reinforcement learning, okay? That is more like the machine trying to make decision as a result of its interacting with the environment. It actually happens when the machine will have to make series of decisions along the line, okay? Now, some people argue that we have the fourth leg, which is the semi-supervised learning, which is more like a blend of supervised learning and then unsupervised learning. But like I said, it is just a blend of the two. So I wouldn't want to include it over here. But depending on how you understand it, you may want to include it to have the fourth leg. But I think distinctively, we have the supervised and supervised and that of the reinforcement. So we are going to look at some basic concepts in building machine learning models, okay? And we are going to look at a very simple linear regression model. So yesterday we were able to do something, okay? I think I have it here. Let me see if I didn't take it off. Yeah, this guy. You see, yesterday we were trying to predict sale increment, and then we said the value for the sale increment is dependent on all of these guys. Now, the same thing applies to what we have here. Oh, sorry. The same thing applies to what we have here. Now, this equation that we've been able to develop, this equation, this guy, this equation here is what we are seeing as this regression line, okay? So that equation is the regression equation, and then it is represented by this line. Now, the red dots is actually scatter plot, okay? The values of X and the values of Y. So when X happens, what happens to Y? So if maybe X is 1, Y is 2, we plot it. If X is 2, Y is 7, we plot all of them. And we'll try to come out with a line called best fit, the kind of line that is able to fit our data very well, such that upon it, we can make projections and even calculate our errors. Now, look at this. You see each one, let me blow it up a bit. Now, you see this line here. Now, the distance between this line and each of the points here is recorded as error. Do you see? So that is what we were trying to explain over here. Where is it? So when we were doing, I think it's this one. Okay, it's this one. Now, the distance between the data point itself and that particular line, the best fit, is the error. Okay, so that's what we have here. You can see we have a particular point over here. Okay, and this is the best fit line. Now, the best fit line is saying that, okay, this value is actually P1, X1, but the actual value that we had is actually Y1, X1. So the difference between the actual point and the best fit line is an error. Okay, so what we'll try to do is we'll try to get the error from this to this line, this one alone to this line, this to each one of them, then we sum it up. Okay, so when we sum it up, that is what we are going to measure as our error term. Okay, so this one here is basically a regression line. Just forget the slope, the tangent values over here. We are not going to pay attention to it in this course. But all I need you to understand is that this guy here is the model. And the model is represented by y is equal to theta 1, where theta 1 is actually the constant, okay? And then theta 2, x. And then x here is the independent variable. And the value, or it's called weight. The weight is the theta 2. So I think we did something like that over here, okay? This guy here is what is represented by the theta. So this can be, and this is the constant, okay? So that is similar to what we have here, okay? So machine learning model can be as simple as you building this regression model, and then we are going to see that in action. So yes, to build a very simple linear regression model, there are a few things you need to do. Now, you need to do the exercise of data pre-processing. And I think we saw much of that yesterday, where we looked at data pre-processing in the light of you bringing your data into the platform, where you start with the data cleaning. Okay. You pulling your data into your platform, where you start with your data cleaning. You try to transform the data. And you even decide to split your data into training and then test sets. Now, when you're done, you have to build your model. So the model is actually the kind of algorithm you want to use. And then, trust me, there are many, a lot of them. if I should open, let me pull up Google and then ask for machine learning models. Okay, if I ask Google to give me a list of, please, can you still see my screen?
Yes, please.
Okay, good. So you can see Google is listing something called decision tree. All it is trying to say is that decision tree is an algorithm that have been built over there. We can use this tree here to, okay, we can use this algorithm here to train our model to give us some predictions. But there are a few things you need to pay attention to. You know, we have decision tree, and then we have logistic regression, we have random forest, we have all of these support vector machines and the likes. Now, why did this one here come into existence? Why did this guy here come? Why did this guy here come? Now, sometimes it depends on the kind of data you are working with. And I'm going to demonstrate that in a moment. We have some models that are good fitting linear regression models. So linear regression, I think you can see from this point that linear regression, you can see that this is linear, okay? It doesn't curve like that. Now, we have some models where the data, when you plot or when you do the scatter plot, it is not straight like this, okay? You can see the data being spreading out like that, more like a curve. With that one, if you try to use linear regression model on that, your model is going to woefully fail. It is going to give you the wrong predictions. So, like I said, we have all of these models there, but let me show you an example of a linear regression model. Okay, now if I check the images, now look at what I have here. Good, I think there's a very good example. So look at this. This guy here is linear. Okay, this guy here is also linear. So you can see that with this data, if sorry. Okay, sorry guys. So you can see that this data here, if I try to draw this linear regression line or this best fit line in this scatter plot, it fits it well to some extent because we can actually get a smaller margin of errors trying to calculate the distance between each data point and the line of best fit. Now look at this one here. Do you think this one here fits the data or does it really describe the data at hand? Look at the data is something like this, it curves. So it is going to be better if we don't look at this data here from a linear regression perspective. But we can look at it from a different perspective. The perspective that fits the kind of a curved nature of the data distribution. Okay. Now look at this one here too. What happens if we shift this line here a bit? And I think it's going to fit it very well. Look at this guy here too. The data looks something like this, and we are trying to fit this kind of line. It means this line here doesn't fit our data very well. Now, the same thing applies to what we have over here. Look, so this guy here looks perfect. It is linear. This one here also looks perfect. It is linear. But this guy here is not linear. Do you see? Because if it is linear, we should be able to draw a straight line. But you see, this is more like a curve in this data set. And this curve fits this data here very well. So sometimes, depending on the distribution of your data, you may want to choose a particular model. So you can go back to your statistics that you did to look at data distribution, where you look at Poisson data distribution, gamma data distribution, and the likes, to look at the distribution of each data set, and then to look for the appropriate model that fits your data. Okay. So yes, what we are going to do is when we pull our data in, we'll try and then process it. Once we are done with the processing, we have to select a model. And then we've seen a lot of models. We can have linear regression, we can have logistic regression, we can have random forest, we can have XGBoost, we can have support vector machine. Well, tons of them, you can select any of them, but you have to understand the distribution of the data, and that is going to help with your accuracy. Now, when you are done building the model, you have to look at evaluating it to check for the accuracy. Okay, so this is more like a loop. If you check the accuracy and then it is bad, you may want to go back to your model to, there is something we call parameter tuning. Okay, you have to tune some few parameters, and we are going to see them in today's session. We are going to be tuning a few parameters to see which one performs better on the data with respect to the predictions. Okay. All right, so the first thing we are going to do is we are going to explore our data and then start with a very simple linear regression model to demonstrate how machine learning models can be built easily. Okay, all right. So this is the data at a glance. So we are not so much interested in this one. So yes, this is how we are going to get our data into the platform. We are going to do that by following on what we did yesterday. Okay. So let me look at this. I'm trying to buy some material and okay. So okay, I think that's fine. So let me try and then create this one. And I'm going to call this, rename this guy here to, let's say linear regression, right? So let's call this guy here linear regression. So the first thing we have to do is we need to get our data in. So of course we need to import the libraries of interest. All right. So we are going to import pandas as PD. Now moving forward, I'll keep coming back to this one to add a lot of libraries to it as and when the need arise. Okay. All right. So now that I've been able to import this, I'm going to leave this guy here for libraries. So I'm not going to add anything here to it apart from only libraries. So I'll need to get my data. Okay. So how do I get my data in? I'm going to call my data a data frame, and that is actually to read a CSV file for me. And that CSV file is sitting right in my working or current working directory. Okay. So I'll show you how to get your current working directory. So this is housing.csv. Okay. And so therefore, if I do df.head or df.describe, okay, you can see some information about our data. Okay, we can have some information about our data. Please, any question on this one? Hello. Any questions on this one? Or we all understand what's happening here?
For me, I understand.
Yeah,
okay,
good.
that's
Yeah,
fine.
good.
Okay, that's fine. So if you look at the account, you can see price, area, bedrooms, and the likes. We don't have any missing value here. These are the means and the minimum to start from 0, which is maybe at the parking. You may have a house without any parking lot like that. So we can also have the maximum. You can have a car with a maximum of 3 parking lots and the likes. So the next thing you may want to do is, of course, you are free to explore the data just anyhow you want, but the focus today is not about exploring our data. The focus is to build a machine learning model. I think we saw more of this yesterday. All right. So now that we have this one here, you may want to check if there are some issues with your data. Okay. So we are going to look at data cleaning. Okay. So we are going to try and then clean our data a bit. In fact, I'm taking you through the step-by-step approach in developing your model. But of course, the first one or the first model we are going to develop is going to be in the simplest form you can ever have. All right. So with the data cleaning, can we check for duplicates? Okay. In fact, I'm not going to check if there are duplicates in there. I'm just going to remove them if there are duplicates in there. So I'm going to drop duplicates. Okay. And you remember what I said that in place does? If I don't do in place this, what I have to do is that it is going to drop the duplicate, but it will not affect my current data frame. So I would want to save this as my current data frame is after I have removed duplicate. Okay, but I don't want to do this one when there is a better way of handling that. I can easily do this and say in place is true. So when you're done, replace it. So with this line of code here, I've been able to remove all duplicates from my data, assuming there is. All right. Now, the other thing is I would want to check if there is any missing value in there. Okay. So we can check for missing values. Okay. So what I'm going to do is df.now.na. And you can see we have false, false, false over here. It means we don't have any kind of issue with our data with respect to null values. Okay. So if you check and then there are some few nulls in there, you understand how to handle it. You can choose to interpolate. You can choose to use the backward fill. Maybe you replace the missing values with the mean of that column. In fact, anyhow you may want to handle it. All right. Then, in fact, we have a lot of things we'll have to check before we go ahead to build our model. But in this case, we know that our data is already clean. Because if I should open this data here, it can go through the entire thing and you wouldn't find any issue with this data. Okay. So I'm doing this one here to let you understand that for any single data you have before you build your model, you need to explore the data like I did a very small exploration here. You need to clean your data before you even go ahead to select the model you want to use to fit this particular data. All right. Now, I think I'm okay with this. Now, the next thing I would want to do is I want to say select. You see from here, we're able to determine that this one here is the independent variable, right? The dependent variable, sorry. And these guys here are independent variables. I hope you understand the difference between dependent and independent variable or predictors and then the predictor.
Yes, Pasty.
Yes,
okay.
sir.
Okay, all right. So what I'm going to do is I'm going to separate independent, or maybe I'm going to select. So do you remember about the feature engineering thing? But there is a whole course on feature engineering. So you don't just look at it and select the kind of columns you're interested in. There is an approach for selecting. But for this case, we are just going to look at the various columns and then select. So we are going to select our independent variables. Okay, so when we are done, we select our dependent variables. Of course, the independent variable is mostly X, and then the dependent variable is mostly Y. Okay, now let's look at the criteria for selecting the independent variables. Now remember, we said we are going to build a regression model. Now regression model here works with only numerical data. Now if you look at this one, let's move to the data set. You see this main road, yes, no, and then things. This is not numerical value, so we can't include this in our model. There is a way of handling it, okay? So you remember, we are in tomorrow's session, we are going to talk about categories, okay? How you can work with categorical data like this, so that we can just convert this one here to numbers. You remember in the opening, I mentioned that so long as the data you have can be converted to numerical form, you can train it on machine learning algorithms. You remember? But you see, this one here is not numerical. So we're trying to build a regression model for it. It will not work. Okay, it's going to throw errors on the screen because these are not numbers. These are also not numbers. So of course, we cannot include these two guys in our models that we are going to build for today. But later on or subsequently, when you get to know that we can easily replace all yeses by 1 and then all no's by 0, it becomes numbers. So therefore, we can include it as one of our predictors. We can also say that we can replace all no's as 0 and then all yes over here as 1s. Then I will include it, but I would want us to pick it in steps. Okay, so today I'm not going to worry you about how to encode categorical data. We are going to focus on only numerical values. Now, the next question I'm going to ask you is this. Before we do this, okay? Now, these are the various columns. Let me include data types. This thing here can guide you. So let me do df dot data types, okay? So the D types is for data types. Now look at this. From here to here are all integers. This guy here is also an integer. But these guys here are not integers. It means for the model we are going to build, we can't include them. We can't include these guys also. We can include only the integer-based values for today. Okay, so this is going to guide us. Now, the next question I'm going to ask you is this. Do you think that the area of the house, not the area as in maybe it's in Kumasi or Takrady or no, we are talking about the space, maybe 100 square something, 200, 150 square something, that's the area. Do you think the area of the land can actually influence the price of a house?
Yes, it can.
Yes, it can. Yes.
It can. So
Yes.
if it can, it means the area is a predictor of the price of a house, right? So we are going to select all of our S's and say area is one of them. Now, apart from area, does the number of bedrooms affect the price of a house?
Yes.
Okay, so if it does, we are going to put it here. So what we are trying to do is anything that contributes to a change in the price of a house is part of our X values. Okay, so in order to let me include the number of I've included bedrooms, right? Number of bathrooms. Does it influence the price of a house? Are there more sisi adan atoto adan mo nkan?
Of course.
Yes, yes.
Of
it is.
course.
I understand. Some of us we don't have nothing, so we don't know. That's why we are falling on you to support us in this regard, to tell us if it actually influenced the price of a house. You know that actually I can look at for all of these things. And you can say a Danny boy 2 million cedis. I can say, oh, it's worth it because this washroom, this number of that. Oh, handy. Mom, thank you. What other thing affects the price? Any other? This one, the number of story, right?
Yes, boss.
One story building would be less than maybe 3-story. I think that makes sense. So like I said, you see, if the house is by the roadside, the price is different from a dire a eponym.
Sure.
Yes.
So that means this guy here can influence the price of the house, but you see, it is not numerical in nature, so we are not going to consider it now, but we'll consider it God willing tomorrow. So if it has a guest room, a basement, water heater, whatever, aircon, a lot. Okay, we have the parking. Does this one also influence the price of a house?
Yes.
Yeah.
Make sure na so film on so.
See, for park your car. And I'll park your car.
Me park or compound.
I say with 2 battery.
A low battery.
Okay, so what do we want to predict? We want to predict the price of the house, isn't it? So all I'm going to do is that I'm going to say that, hey, but remember, I've selected only the columns, but I haven't selected the values. So to select the values, you know what I'll do, right? I'll just do the F like this and pass this guy around it. Does this one here make sense?
Yes, Pasty.
Okay,
Yes.
good. Now, if I need the price, I can do the F dot price, as simple as that. Otherwise, I can do this and then pass the price to it. But as you know, I'm a fan of this one. So we have all of our X values and then all of our Y values. So if I want to see what is in my X, I can do X dot head. And you realize that it is just the columns that I've selected. The rest are not part. If I put Y, can see that it is only the columns of interest, just that single column, which is supposed to be the price. Okay, good. Now, the next thing I'm going to do over here is that I now have my X values, I have my Y values. I want to give this data here to some model or some machine for it to learn that, hey, I found that this is my X. I found that these are my X's, and then I found that these are my Y's. And when the area was this, bedrooms were this, the price was this one. When the area was this and this information, the price was this. Just look at it and see if you can come up with any pattern so that in future, if I give you, I'm going to buy a house and I give you just the area, bedrooms and the parking lot, you should be able to tell me a fair price I should pay. Does that make sense? Okay. So that is what we are going to do here. So now that we have, I don't think we even need this one. Let me take it off. Now that we have this guy and then that guy, the next thing we have to do is we need to decide on which kind of model we want to use. So you remember that over here, we said we're going to build a very simple linear regression model. Do you remember? Oh, where is it? We said we're going to build a very simple linear regression model. Okay, good. One important thing you have to know is that, see, we have a lot of models. A model like linear regression. A model like this is found in a different package as random forest. Okay, it means the team that developed this, they actually developed it and then added it to some folder. So it's more like we have a very big folder for the entire library. And within that library, let's say a library called ML library, just an example. So ML library is a folder. And then within this folder, there is another folder called linear regression and the codes are in. And then we have another folder called random forest and that. Now, sometimes it may be that this guy here is not even in this folder at all because probably it was developed by a different team. So imagine in future, you are an expert in machine learning and then your mathematics and statistics is also good and you are able to come out with an algorithm that is able to predict what is going to happen next. Then you create your own folder. So you may create your folder and say that maybe a Pasty library like that. Okay, and then within Pasty library, I may call something maybe Prophet. You know, Facebook has got an AI model called Prophet. You can use it. It is similar to what we are going to use today. It is similar to random forest and the likes. So I want to create my library, and then my library is going to be called Pasty library and then Prophet. So if you want to use Prophet, you have to use something like import Pasty library dot Prophet. Okay, as maybe PH. Then you use it. Okay. So what we are going to do now is we want to use a package that was written by someone, and that package is called linear regression. But where can we find it? So that is what we are going to do. And that's the reason why I left this space. I'm going to import that guy. So That guy can be found in, I think, from sklearn. So I hope by now you understand what I'm doing with sklearn. I think there is one guy called is it linear model, can import I think linear regression. Okay, good. So we have someone wrote a whole algorithm, but the algorithm was embedded in a folder called sklearn. And then in sklearn, there is another folder called maybe linear models, or there is a class called linear model. And then within this class, we have all of these methods. Okay. Or this is more like the file. And then within the file, we have a function like this. If you remember, when we're doing our own. Remember, we created mathematics, and then within mathematics, we created the add, the subtract, and the likes. So that is similar to what's happening here. So we are going to use the linear regression guy. So in fact, when you type it, you should run it. Otherwise, it's going to throw some errors. Now, it doesn't necessarily mean that anytime you need to import a package or a library, you have to come and write it here. I can decide to write it over here. But I'm just trying to be a bit conventional where I keep all of my libraries at the very top, then the rest of the codes follow. But if you want to import your library here, nobody is going to prevent you from doing that. Okay, so now that I have that, I'm going to call my linear regression, and I'm going to call this my model. Okay, so my model is actually, okay, so let me say model selection. Okay, so once I have the model selection, I can say that, hey, this is my model. And then my model is actually linear regression. So if I run this, let me call model now, and you can see that the model is actually linear regression model. Now, when you're trying to build a machine learning model, what you look at is, you see, you selected this model as the one you want to use. The next thing you have to do, come in. Yeah, hello,
Yeah,
come in.
Pasty, this one they didn't give it an alias, no.
No,
Pasty,
I just
the definition, the
called,
library for the name. Okay.
Yes, I just called the full name.
Okay. But you can't
and
give it
that's
an alias if you wanted to.
No, you can provide an alias as linear regression like this.
Okay.
Okay, so you see, this is the model. I've created it. Now, what I have to do is to pass my data to this model and then ask it to learn from it. That is all. That is my job. So I'm going to say that this is how we ask the model to learn from our data. We try to fit. Okay, we try to fit it. So we are going to fit our x and then y. So by now, you know what x is, right? This is my x. I'm trying to fit. In fact, if I should call x, this is it. I'm trying to fit this entire data here. Then the y, I'm trying to fit the entire column here. So this is what I'm trying to do. I'm trying to fit it. Now you may also want to do dot fit like this. You can call it on it, but anyways, if you do fit and then xy, this is also acceptable. But I try to bring it down to make the code match readable. Okay, good. So at this point, I'm done training my machine learning model. So who thought it was something difficult? Because I'm done training my machine learning model. The next thing I have to do is to do some predictions with it. That's all. Then I check the accuracy. So the machine learning model be building in skirmishes. Anybody with a question? Anybody with a question?
Please, can I come in?
Yeah.
So if I want to summarize what you just did, I went off a little, but at least to summarize it, that means you have to know the type of model you want to create before, right?
Yeah.
Okay.
But what you can also do, you can test different models. You will see that by the end of today's lecture, you see I'll be testing different models. Like after doing
Okay.
the linear regression, I'll pick another model and then test.
Okay, so before when you get the data, you can test the models, or you can specifically know that this is what I want, so I'll use this model because I know this one will go for this, right?
Well, you can't really tell which model is the best.
Okay.
The
Thank
only
you.
thing is that the model performs better when it's able to fit the data very well. So remember I was talking about data distribution, where we have Poisson data distribution. I don't know if you've heard about that before, but let's say data distribution. You can put like a whole list, distribution list. Oh, let me see. I don't know, or data distributions. Oh no, you can get something like gamma data distribution. You can also have normal data. Have you heard about normal distribution before?
Heard
I'm
of
sure
Yes.
that
said.
before.
So normal distribution is also a particular distribution. The distribution is just trying to look at the pattern, what it follows.
Okay.
So we have gamma distribution, normal distribution. In fact, normal distribution, you see that the mean, the median, and the mode, it falls on the same number. Okay, so something like normal distribution, like this. Look at this one. If you have a normal distribution like this, the mean is here, 0. The median is 0. The mode is also 0. They all false. So if you have a data with the same mean, same median, same mode, then you know that the data fits a normal distribution. Now it is up to us to identify or recognize that. Oh, I didn't have an answer. Okay, good. It is up to us to recognize that, okay, if I have a normal distribution, it may fit linear regression very well. But because you have a lot of models, you don't really know. So you would want to test with, okay, let me try linear regression and then see the accuracy or the performance. When you are done, if the performance is say 80%, and you test on a random forest, and random forest performance is say 90%, which one would you go for? Of course, you go for random forest, right? Now imagine you pull in another model, let's say logistic regression, and that one gives you 98% accuracy. Of course, that's all you'll be using. So what you'll be doing is you'll be testing several models, changing some parameters up and down to see what is going to happen. Yeah. So come in.
Yeah, so Pasty, that is it also allowed to, let's say you use a particular model and then you use another model on top of that model? Like you do linear regression, and after that, the resultant, whatever you are getting, you add random forest to it. Something like that. Is that also allowed?
I don't understand, but if I get you well, you can't do that. What you can do is, you see, we just try to fit the data to this linear regression. If I decide to create a new model, let's say model 2, and this model here is a random forest, like this, I also need to do model 2.fit. It should fit the X and then Y. So I'm trying to fit my model to the linear regression, then I check accuracy. When I'm done, I use random forest, fit the same data, check accuracy. So this one you can create, because they all follow the same thing. They all call a fit method. They all call a fit method. So you can create a function, list a lot of models in, check the accuracy for each one of them. And then the best one you select.
Oh, okay.
But moving forward, you get to appreciate it more. I think we just started. That's why this is becoming a bit confusing. Oh, did I remove something? Oh, yeah. Wait, I think I've removed something. My X values and the Y values. Do you see? I accidentally tapped on this one. So let me call my X, and that is supposed to be DF. And that was area and bedrooms think bathrooms, stories, and then what's in room, and I think
Parking.
Okay.
parking.
Pasty, does it mean it doesn't have undo function or something?
Okay, so what I did was I took the entire cell out. But if, let's say, I cut, maybe I take this one. Oh, parking, come. If I do this, I can undo, it will come. But I removed the entire cell. That's the reason why I couldn't get it. Probably it is there, but I don't know how to do it. So,
Okay.
so ysdf dot price. Okay, so we now have these two guys, and then we are able to fit our linear regression model. What we are ready to do is to make some predictions with it. Okay, so let's see. We want to predict the price of a house based on some values of X. So this is what we can do. We can just do model dot predict. Oh, complete it. Okay. We want to predict maybe X, but I don't want to predict all. I want to predict maybe just the top 5, like that. And it is trying to say that, hey, if you have a house with, so let me grab the X dot head. I try to say that the first one, this one, I have a house on this area, this number. So can you predict the price? And then it predicted about 7.6 million. And then the second one is this one. That is what I tried to do. Okay. But this one here doesn't really make a lot of sense. Okay. But I needed to bring this one in for you to understand how easy it is for you to build a very simple machine learning algorithm, then use it to make predictions. Okay. So any questions up to this point? Any questions? Okay.
Pasty, please, can you go over the prediction aspects?
Oh, the prediction is as simple as me saying that this model, I want to predict. Now, in real world, what would you want to do? All you need is, you don't know the price of the house. You want to pass the area to it. You want to pass bedrooms. And it should be able to predict the price. And then we just randomly selected maybe the top 5 values in our data set, this one. We selected the first 5, this one. But then we removed the prices and then gave it area, bedrooms, this one, and asked it to give us the price. And then instead of the first one to be about 1, 2, 3, 1, 2, 3, about 13 million, it was predicting something funny, which is this one. Okay. Now, can anybody suggest the reason why it's misbehaving like this? I can say that the data itself is not linear, okay? And then we are trying to fit it on a linear regression. So it's more like the data that I showed you, the one which looks like a curve, but you're trying to fit a straight line to it. So it will start misbehaving. Okay. So we want to use this one here as the starting point. Then after here, we build another model on top of this one. But we are going to face the follow the exact same processes. Are we okay on that?
Yes, sir.
Okay, sure. Okay, sure. So for everything we've done, I think you can find all of them here with explanations. Yeah, the explanations and what we want to predict and the model selection. So everything. So there is another guy called decision tree. Okay, we are going to use that model, all right, to also check something and then see. And you are going to see something interesting. Then you come to realize that, okay, our data is actually not linear. We try to use a linear regression to fit that model and failed. We now want to use something we call decision tree. Now, this is the rationale behind decision tree. Decision tree is more like this, okay? Assuming someone wants to offer you a job. So this is how decision tree works. It makes decisions at every single point. So it asks several questions like, hey, this one, I want to offer you a job. Then I ask the question of, is the salary $50,000 and above? If it is no, I'll just decline. But if it is yes, I'll ask another question. Okay? Would you have to commute more than 1 hour? If it is yes, you decline. If it is no, you ask. Does the company offer free coffee? If it is no, you decline it. If it is yes, you accept. So this is how decision tree model works like. So if you give it some data set, it will just be asking itself a lot of questions, yes or no. If this is this and this is this, what should I do? Decline, move on, here, just like that. So we are going to look at how best decision tree models can actually fit the current data that we have, because we tried the linear regression and it doesn't fit well at all. Something about 13 million, this guy here is predicting 7 million. Okay. All right. So we are going to try that of decision tree, and it's as simple as doing this. Let me try and then create this one here and then call it decision tree. Okay. So with decision tree, in fact, we are going to do the exact same thing as we did over here. So I'm coming here to copy the code. So let me copy everything here, then decision tree. Okay. But of course, I'm not going to use this one because this is looking at linear regression. I'll come back to that to explain to you what we are going to import at that point. But we are going to also load our data. Okay, so I wouldn't waste time here. We are also going to do what again? Duplicate. We know there are no duplicates. We are not interested in this. We are not interested in this. So I'll just jump to this point. I hope you understand why I decided to jump.
Yes.
Okay. So assuming the data was dirty, you may want to clean it. Okay. So this is what I'm going to do. We are going to import our pandas. When you are done, we load the data. Okay. Then when we are done, we select our X and then the Y values. Now, the next thing I'm going to do is this. I'm going to create a model. But this time around, the model I'm going to create is called, your friend is saying, decision tree. Okay, good. So, we are still going to get it from sklearn. Okay, but in sklearn, this time around, there is a class called a tree. That is what we want to use. So you remember the first one was different from this one. So from tree, you want to import decision tree regressor. Okay, so this is the guy we want to use. So what I'm going to do is similar to what we did initially. I'm going to do my model to be a decision tree regressor like that. Okay, but you know what I'm going to do next? I have to give my data to the model to learn from it, right? So it should fit. I'm going to fit my X and then Y, okay, like that. So when I'm done, I'm ready to do some predictions. So I'm going to say model dot predict. Okay, let me continue myself. Predict X dot head. Okay, good. Now let's look at this one. Compare this one here to the values over here. Now, you see we did the exact same thing here. Let me pull up the sniping tool. Let me pull up this guy. Okay, then let's compare it with this one. See this one? Oh, okay, it's the same thing. This is 5. Okay, this is also 5 by default. Now look at what happened. Okay, so let's try and then look at what is in y.head. I hope that will make sense because we are trying to predict the values of y. So we are expecting this one to be y1, y2, y3, y4. Okay, so let's look at y.head and then compare, do some comparison. Now look at this. This guy here, the linear regression guy predicted that the first y is supposed to be about 7 million. when the actual value is about 13 million. And then look at what decision tree regressor predicted. It predicted exactly the same as this, which is about 13 million. So you can see this guy here is performing better, isn't it?
That's 100%.
Yes, sir.
Yeah. I don't know if someone is confused here. I hope you are not confused.
We are not confused.
Okay, good. So this decision tree regressor was able to predict the first value in the Y, 100%. And look at this guy. This guy here got everything wrong. He failed woefully because he couldn't fit the data very well. Now let's look at the second one. This guy predicted it with 100% accuracy. In fact, it predicted everything with 100% accuracy. This guy here got almost everything wrong. Now that means that this guy here fits our data better than the first one, isn't it?
Yes.
Good. Now let's look at how we can check maybe the accuracy or something. Let's see if we can get something from, I think sklearn has got some metrics, which are good. So it has got some metrics for checking. Let's call the mean square error or the mean absolute error. I think this is fine. Okay. So we are going to check the error margin in our predictions. So let's say that we didn't know this. Okay. So this guy is not there. We try to make some predictions. But sometimes you wouldn't want to predict something like this before you can even check the accuracy. Okay, you can decide to, if you decide to predict for all X, look at the number of values you're going to get. Okay, so you wouldn't want to display the values on the screen like this. So you may want to create a variable and call this the predictions. Okay, so the predictions are now here. If you want to call predictions, of course, it's going to give you the records, but that's not what we want to do. So these are the predictions. Now let's try and then ascertain the error. Okay. Of course, I'm going to hit Shift and Tab to see the kind of values it takes. Now this is saying that what is the true value of Y? So the true value of Y is actually Y. Do you understand? Now, the next thing we have to pass is the predicted value of Y, which is supposed to be our predictions. Is anybody confused?
No.
Okay, so you know our error is simply the actual minus predicted. So that's what's happening. It is just picking the actual value minus what we predicted. And then we want to just check the error margin. Okay. But of course, I hope I was able to explain to you what is happening here. Yesterday, I couldn't do this. The mean absolute error. So the mean absolute error is saying that if we find a difference and the number is either positive or negative, we find the absolute of it and then pick. We just remove the negative symbol off, then we square the value. And that's the reason why we have this big number. So if you decide to square root this guy here, you should get something small. But at least we know that this guy here, as compared to our predictions, this guy here is performing better than the first one, isn't it? Now, the next thing I want to ask is, can anybody tell me the reason why this guy here was predicting with 100% accuracy? Anybody with an idea? Let's discuss. I want us to discuss the reason why that guy this model here was predicting with 100% accuracy.
Can I come in?
Yeah, sure.
Earlier on, you said when you are building a model, we select different types to see the one which predicts the best. So this one, choosing this one predicted the better than the first one.
Yeah. So I want to know, this model here performed better than the first one, but why did this guy here perform close to 100% like accuracy?
So I think our data points are not linear. So if you use the linear regression, you may not get it right.
Okay. All right. So that is an input. Anybody with another thing?
Firstly, I'm guessing based on how the decision tree works, because of how you explained it, it uses a yes or no. So if it looks at the parameters and it doesn't fall in, it ignores it and then goes to the output. So by the time it considers all the parameters, it will have arrived at at least the output closest to the results we are looking for.
Okay, that is also interesting. Yeah, any other person? Or does anybody have got an objection but doesn't know the answer? Like you don't know, but you have an objection. Okay, Nancy.
I don't have objection. I'm just contributing.
Come again.
I just want to contribute.
Okay, sure.
Pasty, you see that the decision trees, the way it's working, it's not easily influenced by outliers. But then
Okay.
with linear regression, the moment you have outliers in your data, it throws everything off. So it makes
Okay.
the decision tree a better way to create the prediction, at least for the type of data we are looking at right now.
Okay.
Well, that's
I think
what I think.
I think that sounds interesting also. Yeah,
Worth looking
very
into.
interesting. Come again.
It's worth looking into.
Yeah, sure. Now, this is going to be my comment on why it was performing better, close to 100%. You see, over here, what is the machine trying to do? The machine is trying to learn from our data, right? At this point. I hope I'm correct on that.
Yes.
Yes.
Okay. So imagine we give the machine, when it is 10, the result is 20. When it is 15, the result is, say, 23. When it is 19, the result is 40. Now, if we ask the machine, when it is 10, what would you predict? What do you think the result is going to be?
20.
It's going to be 20.
20. So why did you say 20?
Because previously when it was 10.
Okay, so all we are trying to say here is that the machine has seen this particular data point before, so there is no way it will get it wrong. Do you see? Because we trained the machine with this same data, and then we are trying to test with that same data the machine has seen before. And so therefore, immediately you bring 10, it will say, oh, I've seen this before. 10 was 20, so it will just give you 20. Does that make sense?
Yes.
So
Yes.
all we are trying to say is that the machine is some way, somehow trying to cheat us in our own game. It have seen, yes, it have seen this particular data before. We brought it and then it was able to predict it with 100% accuracy. You will now go to your company and then say that, hey, I've been able to build an AI model that is able to predict with 100% accuracy. Now they give you a new data that the machine haven't seen before and then it starts misbehaving. Do you understand? So I think, okay, Michael.
So it doesn't mean because the data, we have the prices already. That is why the machine was able to predict 100%.
Exactly. The data has got the X value and then it has got the Y value. So we place the X here and then we place the price here. So now, whenever the machine see this property area, this, it knows that the price is 20. So it actually didn't predict anything. It just went into what it learned. Yes, it went in there into memory to check the things that he has learned, and then it started pouring for us. So it's more like a student doing chew and pour. We'll be sent a question which is in the note. No, if you go, wow, this student is intelligent, he's so brilliant. Give him an application question, one. I don't know if you get what I'm driving at.
Yeah, it makes sense.
So let's look at this. What do you think was going to happen if we didn't put 10 here? That is going to give us 20, but then we place 34 here. The machine haven't seen anything like 34 before. It's now going to predict. This is where the machine is going to reason to predict that, oh, okay, if it is 34, let me say 78. So now that we've given the machine 34 and it predicted 78, we are now going to check on the field that, hey, when it is 34, and you are selling your house, the area is 245. The number of rooms is 5. How much are you selling it? Then Antiajua goes like, it is 80 cedis. Then you now compare what your machine predicted to you as against the actual. Then the difference becomes an error. Do you understand that? So we want to be able to reduce our error as much as possible. So now with this idea, this is what we are going to do. We are going to modify this code here a bit, slightly. So we are saying that, you see, we are using all of the data. We are training the model with all of our data. This time around, we are not going to train the model with all of our data. We are going to split our data into two. One for training. So we are going to give that one to the machine and ask it to learn from this and make prediction. You see that I will predict it 100% again. Then the data that we didn't use for the training, we say that, okay, if you say you are macho, we are giving you a data you haven't seen before. Now predict to us and let's see if you get it right. Okay, so that's what we are trying to do, because we want to use AI to predict the future we haven't seen before. So that is what we are trying to do. Okay, so we shouldn't give the machine the chance to cheat us. So we are going to modify this our code to see if indeed this particular machine is intelligent. Yeah, person be no sure student. So it's like in Ghana where we award people with good retentive memory. I don't know if you've noticed that. All of the students we give awards and everything to, they are students with good retentive memory.
Yeah.
But a student who is able to look at the thing and then reason to be innovative and come out with something else. You see, usually that student will not be scoring that 98 and something. But that student was able to score 60, even though when she had it. So he was just there thinking, reasoning, and danger 60, no. That guy is seriously intelligent. But our system awards good retentive memory and not intelligence. See, and the machine is exposing us one by one. See? So we are going to tweak this decision tree model slightly, okay? So I'm going to tweak it over here, just down here. So let me do this. We see this error, right? Okay, good. Let's say if I run this guy again, okay, let me see. Okay, that's fine. Now let's say that I want to create this same decision tree guy using this data, okay? But I'm going to do something, some small skirmishes, okay? So let me say, we want to split data into training and test set. Okay, so let me change this guy here to a markdown so that, okay, good. So this is what I'm going to do. I'm going to pick this guy. Okay, you don't worry. Let me leave this one and then create decision tree advanced, something like that. Then we'll copy all of those codes and then come here, rename decision tree advanced. Okay, good. Now I'll come to decision tree here. I'll copy everything and give it to decision tree advanced. I'll run this guy and come to this place. I'll read, put it here. And decision tree, I'll come here and put, yeah, I'll come to decision tree advanced. So you see, right after here now, you're training your model now, isn't it? Oh, decision tree. Right after here, you'll be training your model now. But we are going to do some small skirmishes here. Okay, this is what we did initially. So you see this data here, X. Let me create one, X dot head. You see this one? We are going to split the entire data. If I do X dot, and how did you do it? We did something like this guy. Okay, let me get the shape of this data. So look at this one. X is about 545 rows with 5 columns. Okay, now let's look at something here. What I want to do is I want to split this data here into 2, not 2 equal parts. Have you heard about the saying that the more the data you use to train the model, the better the predictions? Have you heard that before?
Yes.
Right. So it means if I train this model here with data points of 100 and someone train it with data points of 1,000, the 1,000 will perform better than the 100. So therefore, we are going to split this data into 2, but not 2 equal parts. We are going to use maybe the one for the training, we are going to make it plenty, and the one for the testing very small. So for example, 80% of the data will be used for the training and 20% of the data will be used for testing, or 90% for the training and 10% for testing. Okay, so this is what I'm going to do. There is one guy called train test split. Okay, so we are going to call that guy. In fact, let's try and then import it up here. So we are going to call from sklen. So that one is within a different package. It's called model selection. So I'm going to import train test split, this guy. So I'm going to call this guy here. Then I'll put it here, train test split. Okay. So what does train test split takes? Now, if you go down here, it is going to give you some information as to what it takes. But basically, it's going to take our X values, which is supposed to be all of this. We want to split all of the X values into training and then test data set. I hope this one makes sense. Hello, are we there?
Yes, sir. Yes,
Okay.
Pasty.
Is
we are
anybody
here.
confused? Is anybody confused?
I think we are good.
Not yet.
All right. Not yet, eh? Okay.
Yes.
In fact, you won't get confused. You won't get there. So I'm going to split the X. You know our X, right? The plenty columns, all of this. Now, I'm also going to split my Y. So that it's going to be like this. I have X that the machine have seen before, and I have Y that the machine have seen before. I'm now going to test with an X the machine haven't seen before, and then a Y the machine haven't seen before. So with the X that the machine haven't seen before, when it predicts, I'll go and compare that prediction against the actual Y that the machine haven't seen before. Do you see? So that we can say that, okay, the machine is performing better, it's being intelligent, or it's being maybe stupid. Do you see? Okay, good. So I'm going to do this. I'm going to pass one other argument to it. I'll call it test size. So do you remember I said I want to use either 80% of the data for training and 20% for test, or you can use 90% for training and 1% for 10% for test. So you can specify that here that hey, I want to use 0.8, which is 80% for the 0.2 for the test. Okay, so this is the amount of data I want to use for my testing. Okay, yeah, I think this is fine. Now, this guy here is going to give me 4 different data sets. The first one is X for the training and then X for testing. The second one is going to be Y for training and then Y for testing. So this is how I'm going to do it. I'm going to do X underscore train. Then I'll do X underscore test. And I'll do Y underscore train and then Y underscore test. And I'll assign it to this one. So immediately I do this. If I should call X underscore train, you see, I split the data now. Okay, now let me call the shape. Oh, shape na my idea. Good. Look at it. The shape of X was 545. Look at 80% for training. Then what happens to the 20%? That 20% can be found in the test. So if I should do X test, you see 100. Okay, so this is the system has been able to break the data down into two pieces, one for training and one for testing. I hope this one here makes sense. Does this line here make sense?
Yes, sir.
Okay. Yeah, Nancy.
Pasty, could you scroll up a little? I want to take a look at something, please.
Come again.
Kindly scroll up. I want to take a look at something up.
Okay. Here.
Okay.
Or I should go up.
Okay,
So
further
X is
up, please.
okay.
All right. Please, let's go back down.
All right, sure. Okay. So we've been able to split our
much.
data into training. So now let's look at this. If I come back to my decision tree regressor, let me run this and run this. Look at the decision tree regressor. I'm not going to give my entire data to the model to see. I say, hey, I'm giving you small data. Just use this one. And that small data, this is the accompanying results. So this is my X and this is my Y. Now, I want you to predict with X test because you haven't seen test before. Does that make sense? Anybody
Yes,
confused?
Pastor.
Anybody confused?
Please, my hand is up.
Okay, Christy, come in.
Please, do you always have to give her the test size, or you can give her the train size too?
Oh, you can decide not to even put it here. The system has got a default size for training and testing, but it just gives you the opportunity to. You can do it like this, just these two guys, and you're good to go.
Okay.
So the system will use the default test. It will split it. So right now, if I check the X train dot shape, you see that it is 408. Is it similar to the first one?
Yes.
So test size.
Almost.
Let me do test size to 0. Let's say 5. That is about 50%.
Okay.
That's what it.
So you
I
bring
think
you want to give us the exact size you want, right?
exactly. If you want to control the size.
But should it always be for the test size?
Yes. So you want to know like train size?
And maybe you can say I want train size of 80 instead of typing
80%.
the test size of 20. Yes.
Yeah. So if it's just the opposite. If you type the test size of 10%, you are saying that you should use 90 for training. Well, but I understand your question. I can't really tell if there is something called a train size. I haven't seen it before.
But it's test size. Okay.
Yes, I know of test size. Okay. Now look at this. We now want to say that, yes, coming.
I think if you press on the shift in the place, it gives you that option of train size. Yeah. I don't know if
train size or more.
Yeah.
Oh, okay. Yeah. That means you can decide to okay, well, I think that's it. You can decide to set the train size. Okay. I think that's true. That's true. We can decide to set the train size. But like I said, I don't really know because I don't remember ever using that before. But it's actually going to be the same thing. If you say train size is maybe 80, 0.8, then you're saying that you should use just 20% for testing. So it's basically the same thing. So you may want to use the train size or test size. Which one of them was better for you? Okay. Now, this one here, we come to the issue of students. So in the class, they are saying that Kwame is the best student. Fine. So Kwame being the best student, Yamani note. Oh, Yama Kwame note na Kwame Ari Baba. It is time for Kwame to tell us the answers. Okay. So we didn't bring our exam question from the note. The exam question was very practical, and Kwame haven't seen that kind of questions before. And so therefore, we want to check if Kwame will be able to predict something for us. So with the prediction, let's see the head. I want to predict with the test head. Okay, so let me call predictions. Okay, so I hope you know the corresponding true value for X test, right? It is supposed to be a Y test, right? I hope you understand that these guys here are supposed to be the same as the Y test.
Yes, sir.
Yes, we are
Okay.
looking for the Y. So.
Now see, best student. First, you see this same model was giving us 100% accuracy over there, but look at what's happening here. 1, 2, 3, 2.4 million. This guy here is predicting 2.9 million. At least it is close, kakra. You'll be surprised that even if we bring a different model like random forest, it is even going to perform better than the decision tree regressor. Okay, but anyways, this is what we are going to do. Let me remove this and say that I want to check overall what is its prediction strength. Okay, but like we did over here, we grabbed the mean absolute error. We'll just come here and then paste the mean absolute error here. Then see that, hey, chairman, this is the actual. The actual is supposed to be Y test. And then you predicted X test. So what is your error? So let's check this error against the error that this guy here gave us and then see what's happening. But I hope you know that we are interested in small error, right?
Yes.
Okay, good. So now let's compare this to our new model. Say the time that we gave this model here, the data it has seen before. Now, oh yeah, guy. We now give it a new data set. That same data set, but look at what's happening. It is making an error of about 1.3 million. Do you see? If you compare this against this, you see this is smaller. I don't know if you can see.
Yes. Yes. This is 65,000 and that one is about 1.
So you can see the issue. The issue is that Kwame is supposed to be the best student in the class, but he's good at when you throw questions from the note, he will score 100% like that. But when you give him application questions where he hasn't seen before, say, hey, now wait there, then this, and that is actually what we have here. So, this is it. We've been able to modify this guy here. I think sometimes when you go through the entire thing can change. Do you see that it has changed to 139? Let's run through. You see, it moved to 134. So it means the prediction keeps changing. Do you understand? Have you realized that it keeps changing?
Yes.
So how do we handle that? We can handle that by, because it is using a random approach to do this. So there's one guy called a random state. We can set it to 0 that, hey, I don't want any funny random stuff. Don't randomize anything. I need just this. So anytime you run it, it should give you, oh, random state no way. Let me check if it's this guy. Test size. I think this guy here should have a random state. It's responsible for that also. So random state, we just prevent it from. One said, anytime we ask it to split the data into training and test, it randomly selects something. It selects this particular one and this one. So we just want to prevent that and say that, hey, for every single time, we need you to grab this same data point. And you can see that it's not changing anymore. I don't know. Does that make sense? See, if we don't restrict this one, when it goes to select 80% of the data, okay, if it goes to select 80% of the data, it randomly selects the 80%. The next time it goes the 80%, it may choose number 1 and number 9 and number 8. Another time it will choose different one. That is random. But if you set the random state to 0, it means if for every single time it is choosing the top 100, it will keep choosing the top 100. Yes, Michael?
So does it mean that if the same data two people are working on, and then you set the random state to 0, although the random state is 0, the data that is going to pick might be at a certain random. It might not be the same.
So I haven't tried this before, but if the random state is 0, I'm supposing that it should get the same response like this error. But if the random state is not set to 0, then your result should be different from someone else's results.
Okay.
And with that one, you wouldn't even be able to know which one performs better. Because at any point in time, it gives you a Oh, sorry, I went off. Okay, please, can you see my screen?
Yes, we can.
Okay, all right. So there is one challenge that we are likely to face, and it is the challenge of, okay, let me demonstrate that to you before we even move on. Now, when I create, yeah.
Pasty, I want to ask a question before you go to the next one. The mean absolute error. So you can only test the mean absolute error on the full test that you've done. Can you do it on just a particular set? Like if you do the prediction on just the top 5, will the mean absolute error still work on it, or it should be the full training data that you worked on?
Okay, so if you do this on, let's say, head like this, the mean absolute error should be on the head of the test.
Oh, okay.
Because this is going to predict 5 values, and you are asking it to subtract the predictions from more than 5 values. So it will get, it will shoot errors.
Oh, okay. Thanks a lot.
Sure. So with this one, there is another guy. Yes, Christine.
Please, the mean absolute error. Is that the only way to test our prediction, the accuracy of it?
Oh no. There are a whole lot of them. Going for we may use some of them or not, but there is even one guy called confusion metrics. Yes, confusion metric. What it tries to do is it will bring the actual data and say that, okay, this one here you predicted it right, and then this one here you got it wrong. It will tell you, it will point it out to you one by one. We have a lot of them. In regression, we have the R-squared score, a lot of them, plenty.
Please, can you go up? I want to ask a question before we leave here. We start the other what we
Here?
Can you go up a little?
Yeah. Or here?
Please, now before where we started the modeling, there's a question I need to ask.
Is it on
Please,
the advanced or the decision tree? This one?
Yeah, it concerns the modeling aspect.
Which is here.
Yeah. Thank you. I wanted to ask, do you always have to use the X as a test? What we want?
This one?
Yes.
Okay. So if I do this, I want to ask this or to clarify things. If you define your function, say subtract, and you say X and Y, and you come to say X, it should return X minus Y. Now, assuming someone wants to use your function, but then what they want to do is to do 10 minus 2. What is the result? We are expecting the result to be 8, isn't it?
Yes.
What if the person does 2 and then 8? What will happen?
We will get negative.
So according to this guy, according to the fit method, you have to give it the X values or the predictors before you bring what you want to predict. So if you hit shift and tab, it is going to tell you that the first one should be your X and the second one should be your Y. Other than that, you can decide to say that, no, I don't want to go by this. I want the train to come first. But this is how you would want to do it. You would want to say your Y is equal to this. Okay, and then your big X is equal to this. Do you understand?
Okay.
That's because the placeholder, the signature for this function or this method is, it takes a parameter X and a parameter Y. So you can specify that my parameter X is this one and parameter Y is this one.
Okay.
But I don't know why maybe you may want to worry yourself about this. I would prefer to arrange it just like how it is so that I don't specify that X is equal to this and Y is equal to this. This will also work fine. It will work fine, no errors. You can decide to also take it. But
so
let's say I do. What if I do Z is equal to this? You see it's blowing up.
Yeah, it will.
It says, what is the meaning of Z? The signature is actually not Z. It was small y. So if I put small y here, it works fine. Okay. I don't know if that solves your issue for you.
Yes, because I'm trying to understand and also see how the formulas are, okay, how we go about it. That's why. So that prompted me to ask the question.
Okay.
Thank you
So
very much.
sometimes when you are confused on what to do, you just, when you open the brackets, put the cursor there, hit shift and tab. It will tell you the signature, what should be here, and then the rest. If you don't really understand what X is, you can read, it provides some information here for you to read to understand.
So this is how to find help in with this, right?
Yes. Okay. So we are going to do something. You see decision tree regressor. Let me hit Shift and Tab. And let me go down. You'll see something called maximum leaf node. You see, by default, it is none. Now, what is the meaning of this leaf nodes? Now, if I come here, look at this one. These guys here are the leaves, the depth. Do you see? Like this one. This is a decision you have to make. It will check if this and this go this, if this and this go this way. So these are the leaves. So you can actually define the depth you should be checking the yes or no, yes or no. You can define it. So
Okay.
let me simply put it somewhere here and say that maximum leaf node is 5. Okay. You see, by default, it is 9. Okay. Let me specify 5.
Yeah.
Now let's pay attention to this. In fact, let me copy and then we check. Look at what happened. The error has reduced to 105 from 112. Do you see?
Mm.
So in machine learning, have you heard anything about parameter tuning?
Mm.
So you have to be tuning some parameters bit by bit to see. In fact, let me increase from 5 to 50. And now let's see something. So this one here was 9. Now let me copy this one. This one was also what? 5, right? Now we are going to check for 50. So let's run for 50 and see. So this is 50, 103. So you can see, I think 50 is performing well, right? You see, 50's error is smaller than this one.
Yes.
Okay, let's look at maybe 500 and see. So as you keep increasing the leaves, it will have a lot of decision to make. We'll check this like about 50 times before it moves in. We want to do that 500 times. Now look at this one. Have you realized that it just increased to 115? It's now even more than this. Have you realized that?
Yes, sir.
Good. So what I'm driving at is that in your quest to tune the parameters to get the best, you see, initially when we did 5 and it got better, 50 it got better, you might be tempted to write about 5,000. Do you see? Because you think it's going to get better like that. But some way, somehow, when we included one more zero, look, it increased the error again. Now, this is the concept of overfitting and underfitting. If you underfit your model, you are not going to get the optimum prediction. If you overfit, you also end up getting issues. So you need the optimum level to predict. Now, the question is, how do I know that 55 or 500 is the optimum level? Of course, one of the ways is to experiment with it, just like we've done here, okay? And that is going to bring us to some concept called, I think we've done all of these things. We split the data, and we've checked the performance. This guy. If you underfit, okay? If you try to underfit or overfit, you are going to get yourself in this kind of trouble. So the best thing you would want to do is to be at the optimum level, or the very point. You see this is coming down here up to this point. This is also rising up to this point. Now, this is more like the optimum level. So the optimum level can either be the level at which the error is reduced, okay? Now, optimum level can also be the level at which it is at the highest point. But if you look at this graph here, we are looking at error, okay? Mean absolute error, the error term, as against the depth of the tree. So if you keep adding a lot of leaves, so this tree here is about a random forest, but we can use it to explain the leaf issue. When we are doing random forest, we'll be talking about trees, the number of trees in the forest, and more like in this concept, the number of leaves for the decision. So you see, because we want to reduce the error, if you underfit, your error is high. So if you keep adding, so look at this one here. At the point where we didn't specify this one, we were at the underfitting stage. Okay, we decided to increase the leaves. So you see the error reduced. So we go to somewhere here, the error reduced. We decided to increase the depth again to this point. So we got here. And so therefore, when we increase it to 50, you see, we got here. So it means, but when we try to increase it again to 500, now look at this. We try to increase this number here to 500. You see, the error has started shooting up again. So we need to be careful to know the optimum level at which we should stop adding more leaves or more trees. Okay. And this is how we get the optimum level. We tried it, we know that this is not optimum. We try this, it reduced. We try this, it reduced. We try this, it increased. So this guy here is the optimum level according to what we have here. Any questions on this particular thing? Does it sound confusing?
So I think the 50 was a random number that was used. What about checking for 60? Or you just check for 3 and then pick the optimal one?
No, you are good to test as many as you want, but once I've used maybe in difference of 5 and I've been able to get an optimum, I think I'm okay with it. You can check for different values, but how long will you be sitting down there checking for different number of leaves? That becomes a bit difficult. You can decide to go in difference of 5 and zeros. So 5, 50, 500, 5,000, 50,000, like that. So yes, Yao and another person wants to say something. Yao and Stephanie.
Yeah.
So let me call
Pasty.
Okay.
Yes. So Pasty.
Yes, come in.
Looking at this, my question was if there was a way to actually get the optimum point at which you know that okay, this is the best value to use. Does machine learning allow you to add like programming, like if statements where you can check and see, okay, test these values. The moment you realize that the mean absolute error starts to rise, go back and pick this value. Does it allow those type of programming things?
Yes, so this is programming, and that's the reason why we're learning Python programming, the if statement, and you can include all of them in here. But we are going to look at one of the best ways to get this value here out. We'll do it with a for loop. Yes, Steph, you want to say something?
Pasty, please, could you go over the whole underfitting and overfitting again? I don't really get it, and I wasn't really, I had to do something, so I wasn't really following. So please, could you go over it again?
Okay. So the concept of overfitting and underfitting is that sometimes in your model, you see, if you understand the concept of decision tree, okay, let me open this guy. If you understand the concept of decision tree, it actually uses the leaves to determine the depth of the number of decisions you should make. So you can see from this end that, okay, it has to test this. This is one leaf. It will have to test this condition. So is the salary at least 50? If you say yes and you want to accept the offer, this is going to be like one leaf. So do you understand that?
Yes, please.
Okay. Now we've specified another leaf. So we have about 3 of them. So we check this and this. We come and check this condition. We check this condition before we even go ahead to accept the offer. Now, in the same way, you know, decision tree checks several conditions along the line. So when we come here, yes, when we come here, when we are about building our model, we can specify the number of decisions you should be making along the line, okay? Or the number of questions you should be asking yourself before drawing a conclusion. Now, by default, the system tries to provide some for us. And that one that the system provided, if we manually try to change it, we ask ourselves the question, does the performance become better? If it becomes better, then it means we were underfitting our model. So that is what brought us to this issue. Now, consider this line here. You know, this is a number line. Somewhere a number line or primary need JHS, Anna.
Yes, we did.
You know, up to now, some people don't know that this is actually a number line. This is a number line with the negatives being here. This is also a number line coming down here. Okay. Now, on this number line, this point is 0, like this. This point is 0. Now, if I move here, I'm increasing it. So maybe this is 0, this is 5, this is 10, this is maybe 15, this is 20. So this is increasing. Now, if I decide to go here, so I'm talking about this is also increasing 1, 2, 3, 4. Now, the values over here happens to be the errors. Now, the values over here has to do with the number of leaves that I'm applying. But I think this model here or this design here is with respect to random forest. And that's why you see tree depth here. Okay. Now, if we come to this point, you realize that when we decide to remove the maximum number of leaves to use, the error was, sorry, this one, 112,000. Anna is, hey, Matthew, let me see. Okay, 1 million. Do you see? The error was 1 million. Now, when we decided to say that, no, we want to specify the number of leaves or the number of decisions you should be making along the line to 5, the error reduced from this point to just 1 million. You see, this one was 1.1 million. The error reduced to 1 million. And that's what we are trying to say here, that if you do not specify anything, this is your error margin. When you begin to increase the number of leaves you have, then the error keeps dropping like that. The error keeps dropping. It will drop up to the point where the error will not drop again. If you tend to increase the number of leaves, the error, you are not going to do anything good to your model. The error is going to rise again. Okay. And we experienced that over here that, look, when we didn't have that, our error was 1.1 million. We increased it to 5. Our error came to 1 million and maybe 5. Do you see? We increase it again, 50. And then look at it, reduced to 103. We decided to increase it again to 500. And look at it. Our error is now increasing. So we said that this guy here is the optimum level. And this guy is represented by this one, this minimum point. I don't know if this answers your question or you are getting confused.
Yeah, I understand the concept. Like, I understand what you're trying to say. But I think I'm getting a bit confused. Is it that with the number the number of like the leaves, is it that like the number of leaves that is being used? Like, what is the default number of leaves that like is being used? What's the default number? That will help me in understanding like if it's too much or if it's little, and then how it affects our error. Like how it affects.
So this is the default value. It was nothing. Do you see? So the system as is working through, try to put something there. Look, me from our classes here. Okay. So the default is this. So look at this. If I decide to remove this one totally, this is the default, like this. I'll run this, and look, it is giving me this error margin. This is very big. So we decided to say that, no, I want to specify my own number of leaves to 5. If I do that, look, the error margin reduced from 1.1 to 1.0. So I'm saying that, oh, maybe if I increase the number of leaves from 5 to 50, my error will reduce further. So I reduce it, increase it to 50 and then check, and look, it reduced. okay, from 105 to 103. So you might be tricked to say that if 50 is better, then you would want to increase it to 500. Now, when you do 500, see, it jumps, it starts increasing.
Okay.
So we say that the optimum level is at 50. So when you are building your model, you have to indicate with 50. So usually you have to test like several of them to get to the optimum point. Okay, I don't know if this one.
But Pasty, you know, from 50 to 500 is like very large. So assuming maybe you move from 50 to like 100, is there a possibility that you would get the error like reducing instead of 50
So you
to
are
500 straight?
Yes, so you are testing. You are testing. Okay, so let me see. From 50, let me go to 100. So you are testing. So 100 give us 109, okay, which is bigger than 50. Do you see? So this is the 50 error. This is 100 error. 50 error is 103, 100 is this. So we can even decide to, can we try 80? 80 leaves.
Okay.
Okay. So 80 leaves is also giving me 107, which is still bigger than the 50. So can I try 55? See, 55 is also 104, which is bigger than this error. Okay, let me try 45. 45 is 100. I think 45 is even better.
Yeah.
Do you see? Okay,
Yes,
good.
please.
So when we tried 45, we realized that 45 even presented a better error than the rest.
The 50, yeah.
Good. So you see, when you go to Kaggle, let me go there. Assuming you are done with this machine learning course and you think you are good enough, and then you want to try some competitions, look at, these are all competitions. So look at this competition, about $50,000 prize. Look at this one too. These are all competitions. Now, assuming you are done, some people have already submitted their results. Some people have submitted their codes already. Look, this person here is done. He has submitted his work. This person is done. He has submitted his work. Like a lot of them are done. So the question is, what will make your model perform better than this person's own? Because they only award the person whose model performs better. So if this person's error is 0.2 and my error is 0.1, I win. Okay, so it is up to you to learn about how to tune your parameters to get the best one. Now, assuming yourself and myself were doing this and you presented your model just like what we're trying to conclude on the 50, okay? You presented, I submitted my notebook and said 50 is the optimum level, and you also submitted 45, like this. Nobody is interested in this 45 or the 50. They are only interested in the error. They will check the error and say that, hey, this guy's error is the least, so this guy won. Nobody will come and then ask you, why did you use 50? Nobody cares. We are interested in a model that performs better. And at this point, when the leaves happens to be 45, the model performs better. We can even try 40 and then see. You see that 40 is increasing.
Yeah.
So this is how the whole thing works. So if you are not careful, because when we keep increasing the number of the leaves, the performance becomes better. You'll be tricked into increasing the number like that, but you fall into the trap of overfitting. If you don't increase it you fall into the trap of underfitting.
Okay, thank you so much.
Yeah, sure. So we are going to do this. We are going to test different levels of leaves to see, just like what we were saying, to see which leaf gives us the better model. I hope that one makes sense. Just like someone was asking if programmatically we can do that. So let's look at this. So this is the code we are interested in, isn't it? Can't we build a function around this one? Define, maybe get error margin. Do you remember how to create functions? I hope you remember.
Yes.
Okay. So I'm going to push everything here into the body of that function like this. Then, because there are some arguments we are using here, I'm going to pass those arguments to this one. The first one is going to be leaves. Okay, so if I do leaves, I have to remove this, the 40, and then put leaves here. So that if someone calls get error margin and then pass 20, 20 will be placed here. If you pass 30, 30 will be placed over here. I hope that makes sense. Now the random state is always 0, so we will not touch it. Then we need to pass the S train and then Y train to it. So let me copy these two guys and then pass it to this one and say that I also need the X test, X train, X test, like that. I think, okay, I'm not done. I'll need this guy also in my function because the only thing I'm interested in is I want to return the error. Okay, so X train, X test, Y train, Y test. Okay, so all I want to do is that I want to return the mean absolute error. If I call this, I want it to be able to return the error for me. That's all, given a certain number of leaves. So if I can say that, hey, I want you to print this one here for me. You know, our X train is the same as the X train. The S test is the same. Everything remains the same, with the exception of the leaves. So let me put 25 leaves here and then print. Now, 25 leaves return 102 errors, okay? So let me return something like that. If I can change this one here to also 30 to check the errors. Now, I can specify a list and then use that list to get all of these things. So let's look at this for maybe index I in a set of numbers. Let me put 10, 20, 30, 40, 50, 60, 70, 80. So let's say this. What I want to do is, please, if someone is confused, you alert me so that we get it right. So I'm going to put I here. So I'm only going to look through to say that, hey, check for 10, check for 20, check for 30 up to 80 on this one, and then give me the errors. Okay, so for each one, I want you to print. When you print I, okay, I want you to include this guy and say that this is the error margin, like this. Look, so at 10, when I is 10, this is the error margin. Is it that the error margin is even smaller for 10? Hello, do you see?
Yes, we see that.
Yes, we see.
Yes, Pasty.
I hope you are not confused with this one.
No.
Okay, good. So I just transferred everything into a function, and then I used a list to put all of the numbers I want to test. And then I had to look through. For each one of them, I want to get the error associated with this number of leaves. And then I print them. So when I'm building my final model, I can now say that, hey, with my final model, I want to specify the number of leaves to be 10. So my final model can be this one. But over here, I'm going to put 10 here because 10 is the best so far. I hope it makes sense. So we use this one here to look for the best model. Now, when we are done, we can use this one here. Oh, return green. You see, so I can use this one here to say that this is the final model I'm going to present to Kaggle for this competition. Because if you put 20 there, you're going to get a very high error. Okay, all right. Any questions up to this point? Any questions? Any questions? Because I'm about leaving you guys to go and then try your hands on some of these things. Okay. So God willing, tomorrow we are going to look at ensemble models and then categorical data. Okay, where we'll be looking at random forest. Then we'll look at some few other models. And finally, yeah, Ima.
Pasty, please, can you help us with the course outline for the Python course? I think we don't have the course outline yet.
The course outline.
Yes, please.
Okay, I can get you that, but I think following the slides should help with that. Yesterday, did I give you the slides for the data cleaning thing, the data pre-processing?
No, no, please.
Oh, I haven't done that yet. Okay,
No,
Only
Pasty.
the
I'll
video.
send that. Come again.
I said we have only the video, the recorded.
Oh, okay. Then I'll send it to you plus this, but I'm going to continue with this slide. I'm going to build up the ensemble. I don't want to create a whole new file for it. I had wanted to do that, but I stopped. So I'll continue with the ensemble models here. Okay. Before I release this much. But anyways, I'll release it to you today so that you can go through this one here to understand what's happening. Then God willing, tomorrow, when I give you the final one with the continuation, you can discard the first one I'll give you, then you use the new one. So please, is there any other question or comment? Okay, if there isn't, then I'll leave you guys for now to grab a few other materials and then explore, because there are a whole lot of things we didn't talk about or we haven't done. So reading other online materials, you know, you can go to Kaggle. The last time I showed you some lessons over there. You can use that material to learn a lot. You can also decide to get some few other videos from YouTube, Udemy, and the likes. That is going to help you shape your understanding of machine learning. All right, so thank you very much, guys. Meet again, God willing, tomorrow in the is it in the morning?
It should be in the morning.
Yes, please.
Okay. All right. So we'll meet in the morning, God willing, tomorrow. And that wouldn't take a lot of time.
Pasty, will you be there? Okay. Online.
Yes. Do you guys want us to meet face to face? No, I'm okay with anything.
Face to face. No, they want it online.
Me, I don't have any problem. If you want us to meet face to face, I can come because
I think the online is much better because of network issues and those things.
But since you are in Accra, please, you come, let's see you.
Oh.
Okay. All right. So we'll meet definitely.
But Pasty, you are traveling this evening. Won't you be tired?
No, I'm not traveling this evening. I'll travel tomorrow.
Because normally the online delays. By the time they set up everything, about 1 or 2 hours is gone. The face-to-face, sorry.
Oh, okay.
So online is better.
Okay, that's fine. Oh, we are still recording.